Up, I think we're on to problem 10. We have to parameterize a circle here. So what do we have? X plus 3 squared plus y squared is equal to 4. So this is a circle that is centered. Let's assume, it's a little bit ambiguous for this problem. Let's assume we're working in 3 dimensions here. The circle is centered at -3, 0, 0. Because we could rewrite this as x minus -3 squared. And the radius is 2, because that's 4 is 2 squared. And it's parallel to the xy plane. So our equation is going to be r of t is... Let's see here. So our circle center is -3, 0, 0. And plus 2, and we'll put a cosine t and a sine t right there. And I think that should do the trick. Let's just give some bounds on t running from between 0 and 2 pi. That'll give us 1 lap around the circle. For part B, okay, now we have an intersection of a plane and a surface, which is a cylinder. So z is x squared plus y squared, and 2x plus 4y plus z is equal to 4. So how are we going to tackle this one? We want to eliminate variables. So let's eliminate z. So that's going to be, let's see here. So if we plug in this in here for z, we'd end up with 2x plus 4y plus x squared plus y squared is equal to 4. And if we manipulate this a little bit, let's see here, I think, so x squared plus 2x, y squared plus 4y is equal to 4. This looks roughly like an equation of a circle. We just complete the square. So we'd like to have that plus 1 there, so this becomes x plus 1 squared. We'd like this to be a plus 4 here, so that becomes y plus 2 squared. So we just added 5 to that. Okay, what's going on? We have x plus 1 squared plus y plus 2 squared is equal to 9. So in the xy plane, this is a circle with center -1, -2. And so circle radius 9 is 3 squared, centered x is -1, y is -2. We'll talk about the z in just a second. So r of t is going to be -1 plus 3 cosine t, and y is going to be -2 plus 3 sine t. And then the last thing for us to do is, what is z? Well, z, remember, z is x squared plus y squared. So z is -1 plus 3 cosine t squared plus -2 plus 3 sine t squared. So that is what would go in here. According to my notes, I'm going to skip these details, but you could simplify that down to 14 minus 6 cosine t minus 12 sine. Oops, I'm running out of room there. Minus 12 sine t. So that finishes off how to do this problem. So how do we tackle it? We did some elimination. We substituted in here. We found what z was. We substitute in to eliminate z from our equation. We just figured out what was going on here. And then we remembered z was x squared plus y squared to get that final component. Okay, so that was problem 10. So that was a throwback to chapter 13. Problem 11 is a 14.7 problem. Find and classify critical points of this function of two variables. So what do we have? We have f of xy is 2x cubed minus 6xy plus y squared plus 4y. We know we want to find critical points, so we need to take a partial derivative with respect to x and partial derivative with respect to y. So the partial derivative with respect to x is 6x squared minus 6y. The partial derivative with respect to y is minus 6x plus 2y plus 4. And so at this point then, we know we have to find our critical points, we need the x derivative and the y derivatives to both be 0. We need to solve this. We need to solve this. So we need to solve the system of two equations. Note that this is not the nice easy case because we have x's and y's in both equations. So we'll start out with this first equation, 6x squared minus 6y is equal to 0. That's 6x squared is equal to 6y. That's y is equal to x squared. So y is equal to x squared. Let's substitute that in now to the second equation. So minus 6x plus 2x squared plus 4 is equal to 0. All of the coefficients are even, so I can divide by 2 and rearrange to get x squared minus 3x plus 2 is 0. Quadratic equation, this factors nicely. X minus 2 times x minus 1 is equal to 0. So I get two possible values for x, 2 and 1. Now we have to find the points here. So we use y is equal to x squared, y is equal to 2 squared, or y is equal to 1 squared, so we get 2 points. So if x is 2, y is 4. And if x is 1, y is 1. So we have just successfully found the critical points of our function of two variables. Now let's classify them. Let's say if they're local mins, local maxes, or saddle points. So to do this, we need to apply the second derivative test. So fxx, we need fxx, fyy, and fxy. So here's the x and the partial derivatives with respect to x and y. So I'm just going to write down the second order partial derivatives. Those are 12x and 2. And fxy is minus 6. Remember, we could find that either by taking the y derivative of f sub x or the x derivative of f sub y. Everything in here is nice, so those are equal. So there's our necessary second order partial derivatives. Now we want to, as we said, classify our critical points. So 2, 4. So remember the discriminant is fxx times fyy minus fxy squared. So here this is 12 times x is 2. Times 2 minus 6 squared. So that gives us 48 minus 36. So that's 12. 12 is positive, so we know we're not in the saddle point case. We're in either the local min or the local max case. And we see that the fxx here, that's positive because it's equal to 24. So that tells us we just found a local min. Because how do we tell it's a local min? The discriminant is positive, and then we have to check the second order fxx, that's positive here. If this were negative, we'd come up with a local max. Let's check our other critical point, 1, 1. So here our d is, once again, fxx, fyy, minus fxy squared. So it's 12 times 1 now. Fyy is still 2, minus 6 squared. So now we have 24 minus 36. That's minus 12. That's negative. So this is whenever our, what am I writing here? Whenever our discriminant is negative, that's when we have a saddle point.